Okay, lesson 1.4 of our calculus content is on continuity and one-sided limits. So we have talked about continuity before, continuity of functions. We're just going to be adding this aspect of limits to the continuity definition of a function. So in the past we've talked about continuity just being smooth and it's not broken. The graph isn't broken at any point in this interval of continuity. So now we're going to look at it a little differently with the idea of limits. So here in this first example, we see three images of why a function might be discontinuous. So in this first one, we see discontinuity just because the function simply isn't defined at a specific x value. So in this case, at c, the function isn't defined there. So that's a hole. In the second situation, we see not just a discontinuity, a hole, but we see the function approaching two different values from different sides of c. The function itself is defined at c. So we could evaluate f of x, we could figure out what that y value here. However, because it's approaching a different y value from a different direction, it's discontinuous. So even if the function is defined at c, it doesn't indicate that it's necessarily continuous there. And then the last one here, we see a hole at one part and the function is still defined at c. So this function is this curve up to c, and then when x is c, the function has a different value. So again, even though it's defined at c, the function is still discontinuous at c. So that takes us to these definitions of continuity, kind of like the requirements that need to be met in terms of limits and a function's value when we're talking about continuity. So these three conditions have to be met in order for a function to be continuous at c. The first one is that the function is defined at c. So that should make sense. Obviously, if a function is continuous at c, it has to be defined for that value. The second would be that the limit as x approaches c exists. So that would address this situation here. So the limit in that middle visual does not exist. Therefore, it can't be continuous there. And then the third one is that the limit itself of the function as x approaches c is f of c itself, meaning you can just directly substitute it in. So these two requirements specifically point to that direct substitution method. Direct substitution. Okay, so direct substitution, those are those situations where I mentioned in class those well-behaved functions. So the well-behaved aspects being the limit exists and the limit is just found by plugging c into the function. Then we have this other formal definition of continuity on an open interval. So a function is continuous on an open interval, a, b, so just from some x value to another x value. It's continuous on that open interval as long as it's continuous at every single point in the interval. So if it's continuous at each point in the interval, on the interval. All right, if a function is not continuous at c, then we've got two types of discontinuities, and these are the discontinuities that we saw first semester when we were looking at them. So hopefully a little bit of a review. First we had removable discontinuities. And those removable discontinuities were the ones that we, in most cases, were holes. Those discontinuities that you could sort of fill in and redefine the function so that we could actually define f of c. And then the second type of discontinuity were those non-removable ones that we actually called essential discontinuities. And let's write that in, essential. And those discontinuities were the asymptotes that we saw or steps, things that could not simply be filled in by defining the function as c. So asymptotes or steps, other examples where you couldn't easily fill in that hole. Okay, so a lot of this is going to be some review right here. So discuss the continuity of each function. So when I say discuss the continuity, I want to know where is the discontinuity and what type of discontinuity is it. So in this case with f of x equals 1 over x. Hopefully by now you can visualize what that function looks like, and you saw quite a bit at the beginning of Math 3, and we've discussed it a little bit in pre-calc. This has a discontinuity that's an asymptote, so that means it's an essential discontinuity at x equals 0. So we would say discontinuous at x equals 0, and it's an essential discontinuity. Okay, looking at example 2, we see f of x equals x squared minus 9 over x minus 3. So as we did when we were studying discontinuities first semester, we actually would rewrite and simplify these functions as much as possible to help us see what type of discontinuity we were looking at. So with this function, we can factor the numerator, that's a difference of squares. So we could rewrite it as x plus 3, x minus 3 over x minus 3. Now we see this common factor here in the numerator and denominator. So this function can actually just be rewritten as f of x equals x minus 3. So this function actually is a line, but it does x plus 3. But it has this discontinuity here at positive 3. So this is a removable discontinuity because it's just a hole. So we've got removable, and that's at x equals 3. So hopefully this is all coming back to you from how we talked about discontinuities during first semester. All right, let's turn the page and look at some examples, new types of examples on the next page. Whoops. All right, so in example 3 here, first of all, we are still being asked to discuss the continuity. So we want to determine where is any discontinuity and what kind of discontinuity is it. So this is what we would call a piecewise function. The function has two different definitions depending on what x is. So let's figure out where the discontinuity is. Looking closely at how this function is defined. This function is defined as negative x, so that's just a linear function as long as x is less than or equal to negative 1. Then we see the second piece of the function, it turns into this quadratic, 4 minus x squared, when x is between negative 1 and 2. So looking at that, think about where the discontinuity takes place, and that would be where the function switches from this first one to the next one. That x value, where the switch happens, is where the potential discontinuity is. In this case, that potential discontinuity would be right here at negative 1. That's the changing point where it switches from one function to the next. So the x value of interest here is negative 1. So that's where the potential discontinuity would be, and the reason I'm calling it potential is because if it jumps in y value from this function to this function, then it's going to be definitely a discontinuity. So in order to figure out if it's jumping from one y value to another, you can visualize it on a graph, but we also need to be able to just do that algebraically. All right, so in order to do that algebraically, let's figure out what the function equals at negative 1 using both of these definitions. So from this first definition of x, f of x equals negative x. So when we plug in, actually I'm going to write f of negative 1. When we plug in negative 1 to our first, that would be plugging negative 1 into negative x, and we end up with positive 1. So the y value in that first, when x is negative 1 in that first function is positive 1. Then when I plug -1 into the second one, I'm just going to draw another arrow down here. When I do f of -1 in the second definition of x, or of f of x, it would be 4 minus -1 squared. And that is 4 minus +1, which is 3. So what that means is there's a jump in y values from each of the two different definitions of our function. That means that our discontinuity is essential. I can't simply plug in, fill in a hole because these are two different y values. So this is an essential discontinuity at -1. Another thing that you could do to visualize this is just sketch a quick graph of this. So if we, and you don't need, I'm going to end up erasing this just so we have more space on here, but if we think about what these graphs look like, so if x is less than -1, less than or equal to -1, the function is the line y equals -x. So that would be the line that crosses through the origin and is negative. So that would be this line, but only that left piece of it starting at -1 and to the left of that. Then at that value, at -1, the function jumps to 4 minus x squared. So if you think back to what that function looks like from Math 3, that's a parabola. The -x squared means it's opening down, and this 4 out front means that it is shifted up 4. So this gives us the parabola, 2, 3, 4, and it's centered here on the y-axis, and then it's got a hole right there at -1. So that's a quick sketch of what this piecewise function is doing. As you can see at -1, this discontinuity here at -1, yes, the function is defined. However, even if I fill in this hole right here, the function is still discontinuous. So that's why it is an essential discontinuity. So I'm going to erase that now and just give us some room for these other examples. All right, let's take a look at example 4. Number 4, we see, again, another piecewise function. So the first thing is to determine where is this potential discontinuity. What is the x value that we see the jump in how the function is defined? So that x value is, again, here we see what the function is going to do as long as x is greater than 3, and then we see what the function is going to do as long as x is less than or equal to 3. So that x value 3 is the x value where this potential discontinuity is going to exist. So to figure out where that discontinuity would potentially be is to actually evaluate both pieces when x equals 3. So in this case, if I plug 3 into that first function, we would get f of 3 equals 3 plus 2 is 5 over 5, so we would get 1. So when we plug 3 in for x right here, it's 3 plus 2 is 5 over 5. So that would have a y value of 1. When we plug 3 into the second definition, we would get 3 squared, which is 9, minus 2 times 3, minus 2. So that would be 9 minus 6 minus 2. Again, that is also 1. So what this means is our function is changing, the rule changes at 3, but it's a pretty smooth transition because right here, the y values, this function picks up right where that one left off. So that actually means this function is continuous at 1, which may seem weird because it's piecewise, but it is still continuous. And I'll sketch a quick graph of this as well. So this is continuous on the entire domain. So if you want a visual for what that function is doing, I'm going to erase this in a minute just again to leave a little bit of space. So if x is less than 3, then this is the function x squared minus 2x minus 2. So what does that function look like? So at 3 is where the switch will happen. 1, 2, 3. And that first one here, x squared minus 2x minus 2, that's a parabola. I'm not going to get too detailed on finding the vertex, but it looks something like that. Whoops, no, it's supposed to go all the way up to 1. So it's got a y value of 1 when x equals 3. And then the second piece is linear. So when x is greater than 3, this is actually x over 5 plus 2/5. So that's a linear function with a slope of 1/5. So that's going to be starting here at 1. It's going to rise really slowly. So that's what this function looks like, and as you can see, while the pattern or the rule or the graph changes at 3, it's a smooth transition because it's defined and they have the same y value there. Okay, I'm going to delete that and we'll look at one more example before we move on. All right, taking a look at number 5. Why does that do that? Okay. So again, the first step is where is that potential discontinuity going to take place? And we can see here that it's when x equals 1. So then we need to figure out what is the function value at each of those spots. So when x equals 1, this top function is going to be 1 squared minus 2, which is negative 1. And then at this second function, for when x is greater than 1, it's going to be 2 minus 1, which is positive 1. So the y value for the first piece at 1 is negative 1. The second piece has a y value of positive 1 when x is 1. This means, because it's not a smooth transition from the first definition of the function to the second, this means it's an essential discontinuity at 1. So it's essential discontinuity at 1. Okay, so these examples just go to show you, even if it's a piecewise function, it may be an essential, it may be removable, or it may just be continuous. All right, so if we do see these discontinuities where the function has a different value from one direction as it does from the other. So I'm going to refer to number 5. So when x was less than or equal to negative 1, we saw this y value at 1. When it was greater than 1, so from the right side, it was negative 1. So just because the limit or the function at 1 had different values, that doesn't mean we can't talk about the limits. It just means that we would need to talk about these limits in terms of from one side only. So that brings us to these one-sided limits, and that's how we'll talk about limits at these discontinuities. So we did talk about one-sided limits a little bit first semester, so just a quick review on the notation is when you talk about the limit of a function as x approaches some value from the right, then we use that plus sign. So that tiny plus sign to the right indicates that you are looking at x approaching c. So if we're looking at a number line here, x is approaching c from the right, meaning coming from those positive numbers closer to c. And then you can imagine that the minus sign here, approaching c from the left, means we're coming from the negative direction. So that would mean we are approaching c from the left. And as long as you indicate which side you're approaching c from, then you can start talking about these one-sided limits. So let's look at a couple of examples here. So in example 6, we're looking at the function x, the square root of x minus 3. But we know that we can't simply just talk about as x approaches 3 in general, because what does this function look like? This is a square root function, and this minus 3 right here indicates that the entire function has been shifted to the right 3 units. So we've got this graph, if you remember what the square root functions look like. So this function isn't even defined for any values less than 3. So imagine plugging in something less than 3. Let's say we plugged in 2, we would have the square root of 2 minus 3, which is negative 1. So the square root of negative 1 isn't defined over the real numbers, so we just can't plug in anything less than 3. So when we think about the limit as x approaches 3, we can't leave it simply as x approaches 3 because it's not even defined on the left side of 3. So that's why we need a one-sided limit for a function like this. And then what we can say is that as x approaches 3 from the right, so we see the plus sign, then the function itself approaches 0. We can also get that value by using direct substitution here, because direct substitution still works because the function is defined at 3. So this limit is 0, which we can see from the graph and we can understand by plugging 3 in. So in this second example, in number 7, we've got another square root function, and we can think about that limit, 2 minus the square root of 2 minus x as x approaches 2. So we can plug 2 in for sure because 2 minus 2 is 0 and the square root of 0 is 0. We know that this limit is going to be 0 because we have the option of doing direct substitution, but it has to be the limit as x approaches 2 from the left only, because this function isn't defined for anything greater than 2. So yes, we can plug 2 in, but we couldn't plug 3 in because 2 minus 3 is negative 1. Or we couldn't plug 2.1 in because it would be the square root of negative 0.1. So in this case, again, the one-sidedness is necessary. And if you want a quick visual of that graph, actually, I'll just use the same axes here. So this one I'll do in pink. And that function has, that would start right here at 2. So the function is defined at 2, but it is going in that direction. So that's why x has to be approaching from the left, not the right. All right, one-sided limits are also useful in describing a function's behavior in a type of function called the, in a function called the largest integer function. And I don't know if you guys have seen these, this symbol or not. These are also called floor functions. If you see that the little notches, they're kind of creating a floor for x. And let me just briefly explain what this function means. So again, these symbols, it's what it's referring to, what this function does. Its output is the largest integer that's less than or equal to x. So these end up creating step functions. So the largest integer less than or equal to x. So when you start thinking about what this function does, let me do a quick table. So x and y, and when we're thinking about, when I plug in 1, what's the largest integer less than or equal to 1? Well, that would be obviously 1. Let's do 1.1. What's the largest integer less than or equal to 1.1? The largest integer less than or equal to 1.1 is 1. 1.2, the output would still be 1. It's the largest integer less than or equal to 1.2. So on the graph of this, if you start thinking about what this graph would look like, we've got when x is 1, y is 1. When x is 1.1, so this is going to be 2, this is going to be 3, this is going to be 4. Okay. So even if I go slightly above 1 on the x's, the output, remember, is the greatest integer that's less than or equal to whatever decimal, and that's going to be 1 the entire time. So this function actually looks like, okay, let me just put a few more examples. When x equals 1.5, the largest integer is 1. When x equals 1.9, the largest integer less than or equal to 1.9 is still 1. So what we see is this kind of leveled out step here, but then when I get to 2, the largest integer less than or equal to 2 is 2 itself. And then all the way up to 3, it's going to be that level, because 2.5, the largest interval less than or equal to 2.5 is still 2. When I get to 3, the function value jumps at 3. So the largest integer less than or equal to 3 is 3. And then it still stays at 3 all the way to 4. So this is the step function created by the function in this example. Okay, hopefully this is making sense. Don't get too caught up on the largest integer function. It really is a simple concept when you think about, the outputs always are going to be some integer less than whatever number you just plugged, less than or equal to the number you're evaluating. So that's why we need one-sided limits here, because in this case, we want to talk about as x approaches 3 from the right. So as x approaches 3 from the right, the function of the value is, or the value of the function is 3, as we can see from this graph. So in this case, the answer is 3. But when we look at number 9, we're evaluating the same function, but that's the step function, or that floor function, the largest integer less than or equal to x. But as x approaches 3 from the left, that limit is definitely different. So if we look at it from the left, x is approaching 3 from the left, that would be a y value. The limit is 2. Because if x is less than 3, the largest integer less than or equal to that number less than 3 is going to be 2. All right, let's look at a few more examples here. So why is this word still... Okay, I don't know why that continuous word is just floating along with us. That's fine. So in terms of the existence of a limit, now you guys are going to have to pay close attention to the symbols after the number. So if a limit exists at C, then it's the same from the right as it is from the left. So if it exists at C in general, not indicating from the right or left, then it means it's the same from the right and from the left. Otherwise, it doesn't exist at C. Okay, a couple examples here. Find each limit. The limit in number 10 as x approaches 2 from the right of the function square root of x minus 2. Our function is defined at 2. We can simply plug it in. Again, this function is the square root function scooted over 2 to the right. So we definitely can see the limit exists as x approaches 2 from the right, and that would be 0. In number 11, we're looking at the limit as x approaches negative 4. And a quick sketch of this graph, the square root function x plus 4 is the square root function, but it's been shifted left 4. 1, 2, 3, 4. So here's a quick sketch. My caution is for problems like this. This is saying what is the limit in general as x approaches negative 4. So this function does not exist for any x values less than negative 4. So since the only direction we can approach 4 from is from the right, this limit as x approaches negative 4 in general actually does not exist. In order to write that the limit is 0, you would have to say the limit as x approaches negative 4 from the right, then we could say that it was 0. But the notation as it is in this problem, this limit doesn't exist because we didn't specify from the right. So it's a pretty small like semantics issue of semantics, but it is important to pay close attention to the notation. All right, so I'm not going to do all of these 6 examples here, but I just want to point out a couple things, and then we'll just do a few of them before moving on. So now that we know what this symbol, this floor function symbol, the greatest integer function that we see in 12, 13, and 14, the value of this function changes at every integer. So if you remember from the previous page, this function, the greatest integer less than or equal to 0, between 0 and 1, 2, 3 is 0. Then at 1, this function jumps. And then at 2, the function jumps. And then at 3, the function jumps. And then at 4, and so on and so forth. So anytime you're looking for a limit of the greatest integer function, if it's not specifying from the right or from the left, then the limit is not going to exist, because at every integer, the function is different from the right as it is from the left. So in these two cases, 13 or 12 and 13, those are values that we could evaluate, the limits we could evaluate, because it is specifying from the left here on 13 and from the right here on 14 or 12. At 14, however, you're told to find the limit as x approaches 2 of the floor function of the greatest integer less than or equal to x minus 4 as x approaches 2 in general. We know that that limit is going to be different from the right as it is from the left. So without even doing a lot of work, we can say this limit does not exist. We could go ahead and find the limits of 12 and 13. I'm going to move on because I just want to do a couple of examples below these. So 15 is one we could definitely think about. So we're looking at the limit as x approaches 3 of this absolute value of x divided by x itself. Do not forget about those initial properties of limits. We could think of this as the limit of the absolute value function of x divided by the limit of x itself as x approaches 3. So these are still as x approaches 3. I just didn't write it. And both of these functions are defined at 3. Both of these functions are continuous at 3. So we can just apply direct substitution here and take the limit as x approaches the absolute value of 3, which is just 3 itself, and the limit of x as x approaches 3, which is 3 itself. So this is simply 1. And we can apply that same logic to 16 as well. Okay, and I know these floor functions can feel intimidating. Don't get too caught up in these. I want to just, the important thing is that you understand how to generate a simple graph of this function. But it's useful in finding limits like we see in 16. So again, just like in 15, I'm actually going to think of this as two separate limits. The limit of this greatest integer function divided by the limit of the function x itself. And again, both of these are as x approaches 3 from the right. Okay, so I can evaluate each of these limits separately. So I know that the limit as x approaches 3 in my denominator here of the function x itself as x approaches 3, that's just going to be 3. So I don't need to apply any of the greatest integer function to that. But now when I'm looking at the numerator, remember, let's draw a quick sketch of this. This will be useful in part B as well. So from 0, the integer, greatest integer less than or equal to 0 for all of these values between 0 and 1 is just going to be 0. At 1, the function value jumps to a y value of 1. And then it stays flat until 2. And then again at 3, we jump up to 3, and it stays 3 all the way up to 4. So as x approaches 3 from the right here, we can see that as x approaches 3 from the right, the limit is 3. So this overall limit ends up being 3 divided by 3, which is 1. So now I want to jump straight over to example B, except, sorry, I was trying to move some of that writing up, but I can't. Let me get a different color here. Okay, so as x approaches 3 from the left, again, I'm just going to arrow and rewrite this down here. I can think of this as two limits divided by each other. The limit of the numerator, which is the greatest integer function, as x approaches 3 from the left. So visualizing that on the graph, as x approaches 3 from the left, our function value is actually still 2. And then as x approaches 3 itself from the left, that's just 3. So the answer to 16b is 2/3 when we're approaching 3 from the left. When we're approaching 3 from the right, it was 3/3, which is 1. So again, this is kind of the extent that I'm going to take the problems to in terms of the greatest integer function. Hopefully you're not too overwhelmed by that at this point. All right, this next definition here is just another formal definition of continuity on a closed interval AB. So continuity on a closed interval AB, so if you want a visual for that, we are talking about from some A value, it's the closed interval, meaning it includes the values A and B. So if it's continuous on the closed interval AB, then on the open interval, it has to be continuous. And the limit as x approaches A from the right is the function value at A. So that would mean the limit as x approaches A from the right has to be the actual function value f of A. Likewise, as x approaches B from the left, the function value needs to be the same as f of b. This is just the formal definition. Don't get too hung up on it. We just include all the formalities in our notes as you're used to by now. So we can apply that definition of continuity on a closed interval in these next couple of examples. So I'll leave that visible. In number 17, the function f of x equals the square root of x. This is asking to discuss the continuity of this. Well, this function is defined only for x being greater than or equal to 0. So that would mean it's continuous if we're discussing the continuity. So this is continuous on 0 and including 0 to infinity. And we can say this now, kind of applying what we saw up here. We can say that because the limit as x approaches 0, so that's, we're talking about as x approaches that the end of the closed interval on the left, the limit of our function at that point is the exact value when you just plug in 0 to the function itself, which is 0. So again, the important thing here is that we're talking about the limit as x approaches 0 from the right. This is what I care about you communicating. You can tell me where it's continuous. You don't necessarily have to be able to explain why every time, but as long as you can discuss continuity, this is just applying that formal definition to an example. Okay, we are going to stop this section of this lesson right now. I'm just going to split it into 2 halves. So at this point you can stop and then there will be a second video for the remainder of 1.4.